Welcome everybody. Today we're going to discuss the normal distribution. In fact, we're going to discuss the standard normal distribution. So let's get right into it. Example 1, the standard normal. Well, before we go much further, I would like to draw a normal distribution, the picture of a normal distribution. And what it looks like is the following. What we have here is we have the x-axis, the real-life x-axis, and above it we have this curve called the normal curve, the z-curve. And this z-curve is a beautiful model for many, many applications. So what I assume is you collect your data from your study and you build a histogram. And I hope your histogram does a pretty good job of fitting inside this picture. That's the idea. It may not fit perfectly, but it fits inside the picture known as the z-curve, the normal curve. If it does, then we can utilize the normal to approximate probabilities of your data set. That's the whole idea here, is we have this data we collect. We hope when we build the histogram, the data looks roughly normal. What it means to be roughly normal is it looks bell curve in shape with a high stack in the middle and low stacks left and right. Very symmetric, as you would call. If your data looks normal, we can utilize that we know the normal curve very well, and we can find probabilities associated to your data utilizing the normal curve. So the normal curve, the standard normal curve, is a very special normal curve. It's a curve whose mean is 0. If a picture is symmetric, the mean and the median will be right in the middle together. Typically, in the middle of the distribution is the median, I know. But if you're a symmetric picture, the mean and median will be in the same spot. It is when your picture is skew that the mean will differ from the median. Again, the median is usually in the middle, but in this case, when it's normal, the mean and the median line up nicely. And we also have the standard deviation. The standard deviation is a measure of spread, and that's very, very important when we discuss the normal curve. The normal curve has, the standard normal curve has a spread sigma of 1 unit. So each one of these spreads is 1 sigma long. And very importantly, the standard curve goes on forever. So this could be a 4, so on and so forth. The standard curve goes on forever. The standard normal curve, the z-curve, as we like to call it, goes on forever. The spread of the standard normal curve is 1 unit wide. So what we talk about is how much area or probability can be captured within 1 standard unit or 2 standard units or 3 standard units, so on, such forth. Now, if your model is truly standard normal, that is the z-curve, then it fits perfectly underneath this data stream right here. Now, if it is standard normal, we have some cool things about the fact that it's a z-curve. The fact that it's a z-curve tells me something very, very important. It tells me how I can find areas. For example, let's say I would love to know how much area is bounded between -1 and 1. That would be an awesome thing to know. How much area fits right there? What is that area? How much area fits right there? I would love to know that. That would be the area between 1 and -1 in the z-curve. That's really what it is. It's the area between the 1 and -1 z value. Well, area is nothing more than calculus. That is, you can find area by using calculus. Calculus in this case would be the integral, because that's how you find area, by an integral, of -1 to 1, the z-curve dz. Now, one would think this integral is easy, but I have not given you the formula for the model. The formula for the model is not that bad. It's a negative exponential. But the ability to do this integral is very limited unless you've done some Calc 2 and some Calc 3. It all depends on when you've learned about Taylor series and understand how to do improper integrals. If you've learned how to do that, then you can integrate this. If not, this integral is very, very cumbersome to do unless we have a trick, and that is called a computer. A computer can easily calculate out integrals. Excel does a great job of calculating out integrals for us. And so this area, which if we had to do it by hand, would be very, very cumbersome, and only to those people that can do Calc 2 or Calc 3, can be done by pretty much everybody. So again, the question is, how much area is in this red region? Well, the great thing about that is we know this area very well, and we actually have a rough answer to this in this case. We know this area is 0.68 units. That's how much area is in there. Now, to understand what it means to be 0.68, you have to understand the picture. To understand the picture means you have to understand one of the coolest facts about the normal picture. If you took this area underneath the z-curve from negative infinity to infinity, the whole darn picture, and you try to find the area of this whole darn picture, the area of the blue is 1 square unit. All right, it's 1 unit in length. That is, it could be 1 square unit, 1 mile unit, whatever the units are, it's 1 unit. It fits into a 1x1 brick, and that is pretty cool. All right, and again, that's another thing Calc 2, Calc 3 could teach you. I'm here more about understanding that underneath the normal curve, if your data fits underneath the normal curve, and the fact that the area can be easily identified by integration, those two link together to give us a cool little idea. That is the normal curve, standard normal. I want to be very clear. The standard normal curve has some really key simple principles. For example, the area between -1 and 1, if we do the calculator for that, if we do the calculus for that, the area between those is 68% of the entire picture. And that's just a number we memorize, because when we do applications, we get to state that between -1 and 1, and what does that mean? Between 1 standard deviation from the center, because remember, this is the mean, this is your average right there, the mean. 1 unit from average plus 1 unit from average minus 1 unit from average is 68% of the population. How do I know that? Because again, if I built my histogram and it fit underneath here, I'm going to use the normal picture to approximate my probabilities. And since the area under this curve is 1, we can utilize the fact that pieces of this will be roughly a percentage of 1, so a probability, or 68%. In this case, from -1 to 1. From -2 to 2, we get an even cooler idea. From -2 to 2, we learn that 95% of the population fits between -2 and 2 on the z-chart. What that means is, again, 95% of the population. So if I study 100 people, their IQs, their heights, their weights, their incomes, whatever you're trying to study about them, is going to fit, 95 out of 100 will fit between -2 and 2 when it comes to standard deviations from the center. If, again, you get to use the normal model. And to me, the coolest thing in the world, 3 to -3. 99.7% of us, and that's just amazing fact to me, 99.7% of the picture is between -3 and 3. This picture does go to infinity, just like the x-axis. The area under the curve does go to infinity, but the amount of area that's actually above a 3 is really, really small. The area above a 3, and conversely, because of symmetry, the area below a 3 is a total of 0.3. Think about that. If the area between -3 to 3 is 99.7% of the area, that leaves a total of 0.3 for both edges. Because this picture is symmetric, and symmetric means I can cut it in half and it be carbon copies, I know that 0.15% of us will only fall above the 3, and 0.15% of us will fall below a -3. That is amazing. Those are what we call the extreme outliers, because think about that as a probability. What is 0.15%? Well, that's 15 out of 10,000. So 15 out of 10,000 will have the characteristic that exceed 3. Whatever you're studying, whatever average you're studying, most of us will fall between -1 and 1. Almost all of us will fall between -2 and 2. Only 15 out of 10,000 of us will have the height, the income, the weight, the IQ to get past a level 3, the standard deviations from the center. And that's what the Z represents, how far you are in standard deviations from the center being 0. This picture never changes no matter what application you do. So these 3 numbers we just memorized, 68, 95, 99.7, they kind of give us an idea of where most of us will fall in life. Cool. So let's now, after we talked about the general picture, let's get to the questions, shall we? So question 1, what's the probability Z is less than 1.12? Well, on my master picture, 1.12 is just about here, a little farther than this. I want to know, what are the odds we're going to be less than 1.12? What I would do is I would shade less than this and think about how much area is in this picture. If I put a 1.12 bar up, how much area would be less than this? So let's think about this. Probability Z is less than 1.12. Well, what I would do, I'd draw a quick sketch. You're going to see this from me constantly in the videos on normality. Is I'm going to put a bar roughly where Z of 1.12 is. And I'm going to ask the question, what amount of area is to the left? It's very important to understand this bar right here represents less than. We have to understand that sentence. That is the less than symbol. Less than means the area below the bar. The area and probability match when you're looking at the normal curve. That's really, really cool fact. The area and the probability match perfectly. So if I can calculate this area, which I can by calculus, I can calculate this area. Once I calculate the area, I found this probability. The good news is there have been many, many tables built called normal tables, all right? These are standard normal tables. And what these are is the computer has built and done the integrals for many, many scenarios. You just got to read the table you have. It's very important. I need to pause there to make sure that's clear, because there are many tables that do areas to the right, areas between, so on and so forth. I'm going to do the area to the left. Everything I like to do in my videos are areas to the left. So I made sure I got a chart where the area is to the left. Now, what was the Z value again? It was 1.1, correct? But it was 1.12. And that second decimal is the column header. So 1.1 and 2 decimals, that is 1.12, is this number right here. So again, I went down to 1.1. That's 1 decimal. Go across to the second decimal, and that's 1.12. And it lines up to the number 8686. That's very important to me. What I first do in any probability picture is, first thing I do is draw a quick sketch. Second thing I do is, if you have the Z value, I go right to the table. And the table will give me or present with me a number that's useful. And in this case, one more time just to verify, it is 8686. Now, what does this number represent? That's why you got to understand your table. The table is always the area to the left. All right? The table is always the area to the left. So step 3 is my pause moment. Step 3 is the, are you sure you want the area to the left? If that is truly what you drew in step 1, then you are done. The answer is 86.86% is that probability. That is, this area here would be 86.86% of the picture. Again, one more time. The table gives me the probability or the area to the left of the bar you put down on your normal picture. So this blue region and the shaded region I want match, and so that's why this is the answer. This is roughly 86% of the picture. And so that means my answer over here by the table will be 86.86%. Done. We move on. All right, part C. What if I want the probability z is greater than negative 2.08? All right, good question. Back to work. So I want the probability that z is greater than, let me check one more time, negative 208. First thing I do in my first step, draw a picture. Draw my normal picture. Roughly think about where negative 208 is. How do you know? You go back to your master picture and think about negative 208 is slightly to the left of this green bar. Okay, so negative 208 is pretty far out there. Got it. And so one more time, what area do I want? Which way do I shade? Well, I look at this symbol. This symbol is greater than. Since that's a greater than symbol, I will shade to the right. And at first glance, I know this area is pretty big, okay? This is a pretty big, good chunk of the picture. We got to keep that in mind when we look at our next step. Because when I go to the table, and that's what I do, when I go to the table, let's see what negative 208 gives to me in the table. So one more time, we go to the table, negative 208, the negative side of the table. Negative 2, got it, O. Then I got to go across to 8. So if these go up by 100 each time, this would be 20, negative 201, negative 202, 03, 04, 05, 06, 07, 08. This right here would represent negative 208 in the Z value. And the table value would be 0.0188. So 0.0188 comes from the table. Okay, so this is why I always put in step 3, called the pause answer. First of all, these numbers in that table represent areas and represent percents. The percent I'm looking at is 1.88. So this is why I put the pause moment in. The table gave me 1.88%. There is no way that shaded area looks like just under 2% of the picture. I got to make sure I, again, understand the table. If I don't understand the table, I'll never be able to answer any question about normality. Again, this table, and every table is different. In this table, it was area to the left. That makes more sense to me. The area to the left is a very small little area. The area to the left, or the percent of the picture to the left, is a very small number. It's 1.88% of the picture. That's great, but that's not my answer. Well, if I know the area to the left, then I know the area to the right. Because together, the left and the right area add up to, you got it, 100%. So if I want more than, I would do 1 minus the table area. And that would be the total area I'm looking for. What is that? 0.9. Let me get my calculator out so I don't make a mistake with you guys today. 1 minus 0.0188. That gives me 9812. So 0.9812 would be the answer I'm looking for. Typically, when I'm looking for a more than question, I do this magical 1 minus. Again, why am I doing 1 minus? Because the blue area is the area given in the table. I want the area in the black. the area in the black plus the area in the blue is 100% of the picture, better known as 1 in decimal form. So if I take 1 minus the percent in the blue, I get the percent in the black. So 98% is the odds. What are the odds? Think about what we're doing here. What are the odds your Z will be greater than negative 208? Pretty dang good. 98.12%. What does Z represent? A mark. How far you are from the mean. This person is trying to be greater than two steps away from the mean on the left side, the below side. What are the odds somebody's going to be above this marker? Pretty dang good in everything. I don't care if it's height, weight, IQ, reaction time, money, whatever you're looking at. As long as the data that you plot fits underneath this picture, I know whatever this bar represents, there is a pretty darn good chance all of us are going to clear this bar. Only a small fraction of the world's population, or whatever population you're studying, is going to fall below a negative 208. That's why whenever I write in this class or whenever I talk, I think about outliers. I think of outliers being below a negative 2. And that's just a classic definition going back to this picture. Anything below a negative 2 or above a 2, there's not much there. I think of the fact that there really isn't much left. If 95% is in between the 2 and negative 2, that leaves only 2.5% of the population to be below and above it due to symmetry. That's why a great, quick, classic definition for outlier is anybody 2 standard deviations below average or 2 standard deviations above average. All right. So we got the answer to this question, 98.12%. So from the table, we get 98.12%. Awesome. Now, of course, these tables are preloaded into Excel, and that's great. You just got to know how to bring them out. It all depends on which way you've taught, though. If you need to learn to use the table, keep working on the table. If you have a computer package, learn how to bring the normal out of the computer package. It's in pretty much every preloaded package. Just got to know the package you're using and then look it up. For me, I utilize Excel. So in Excel, it's under the norm. So the norm brings up so many options. And the option I really want you to focus on is SDIST. The norm period S period dist. There's many other options, but the norm SDIST is key. It follows along in my lecture. So first, I'm pausing because I want you to see what it asks, Z and cumulative. Z being, what is the Z value you're drawing? Well, the Z value we drew was 1.12. Okay, do you want me to add up the area less than it or not? In our case, in the normal distribution, we always want that. So we always want a 1 at the end because we want cumulative. If it was a discrete distribution, we might not want that. Please check a look at my previous videos on binomial and Poisson to see when I switch from 0 to 1 on the back end. For the norm SDIST, I'm always going to want a 1 at the back. I'm always going to want the cumulative because the cumulative turns on the integration technique and I can do the integral which I want. And notice, they match perfectly. In fact, I get more accuracy because Excel is doing the out to as many digits of accuracy as you want, where the table has only done 4 digits. So it depends on how much accuracy you need. Now this one, let's see how norm SDIST works again. So norm SDIST, please, I know there's other ones. This is the one I utilize. It says put in the Z value. All right, negative 2.08. Are you sure you want cumulative? Yes, always here. You always want to add up the area. Boom. Uh-oh. That doesn't match this answer. Well, again, you have to understand your package. Norm SDIST finds the area below. If you want the area above, you have to think. If the area below is 1.8%, then the area above is 1 minus. And so the area above the Z value of a negative 208 is 0.981237. So what I always do is I think about what is my Z value first. In part B, it was 1.12, and that's not a percent. Negative 2.08 is the second one. And let me change the format here because these are not percents. They're just general numbers. So this is 1.12. And this is negative 2.08. And so when you have your z-value, norm s dist will look into the table, or in fact, it actually builds the integral. The table is only done out to 4 decimals. Excel will do it as many decimals as you need, the integration. Again, the integration here would be from negative infinity up to 1.12 because we're doing below. And so there is your true area, the true probability. Below it, again, if you did negative 208, this would be the area below. But just like I did in the previous question, or in this question we're working on, if you want above, you want 98%. And again, the greater than symbol means you are looking above. With this, you can answer any question. You just got to understand how to work with either the table or the norm s dist. All right. Now let's look at this question, part D, negative 134 to 145. Negative 134 to 145 is our next question. So we want the probability of negative 0.134 to 145. How to do that? And let me just make sure I got the right numbers. 134, 145. Well, I don't like to change my steps. That's what I wanted to say. I like to keep the steps the same. I like to imagine my area. So when I get my number, I'm not too shocked by the number. So this area is roughly that shape. And so when I get an answer, I know it's not that big, somewhere in the 70s, okay? Why? Because if I go from negative 2 to 2, that's 95% of the picture. So I know it's got to be under 95%. How much under 95%? We're going to find out. So I want this area. Now, you could go to the table for both. And in fact, I want to do that one more time to show you what you could do. So you go to the table for both. And that's what I'm going to do. I'm going to the table for both, just so you got practice with the table again. So we're in the negative one. So negative 134. Negative 1, 3. That's 0, 1, 2, 3, 4. Negative 134 would have a 0.0901. So 0901 as its answer. 0.0901 in the table. Vice versa, if I look up in the standard normal table, which you can download anywhere, just make sure it says area to the left. That's very important. What was my number I'm looking up again? 145. 14, go across to the column of 5. 145 lines up at 9265. Now, what the heck does the table give us? Well, one more time, let's discuss this, because that's the key ingredient. What does the table actually give you? Well, it gives you an integral. Great, but if I don't really understand calculus, what does it give to me in general? Well, what it gives to me is the area below a bar. So this blue area is roughly 9% of the picture. That's what I know. And because my histogram would fit underneath this picture if it's a normal histogram and my data is normal, that tells me 9% of the time, whatever data flow we're looking at, 9% of the time it's below a negative 1.34, whatever that represents. And in future videos, we'll look at that. We'll get into applications and show you how to turn an application in from the Z table. That's very important. All right. Right now, we're just working on a very generic standard normal. So the table, the green, what does that represent? Well, that represents, again, the area to the left. So that would be this green area right here, all the way down. I need to make that very clear. The green area is the area all the way down from the left of the bar. The blue would be the area to the left of the blue bar. But that's not what I wanted. I wanted the area between again, the black area that I had highlighted between. So the question is, how do I, and that's why I always put step 3 in, the pause moment, how does one find the area between? And I'm pausing because I want you to think about that. How would I find the area between the two? And hopefully you see it. If I take the green minus the blue, I get the black area. And so if I want the between, I'm going to take the green area. I want to verify something. 145, 145, 145 is 65. My handwriting got a little sloppy there. That is a 6. So it's 9265 minus 0.0901. That number would be the area of the black region, and that is the area that I'm looking for. So 0.9265 minus 0.0901 is a whopping 8364. And so that's the answer. Roughly 83% of us will fall between those two markers. What are we studying? Whatever fits underneath there in terms of a histogram. As long as your histogram is normal, you could talk about that fact that 83% of us, 83.64% of us, will fall between these two bars. For height, for IQ, for weight, for GDP, there's a lot of things that are normal out there that we measure with the standard normal. So there's a lot of amazing facts, and please stay tuned for future videos to see that. So cool, our answer is 8364. So from the table, in my work, it's 83.64. But okay, how do I do this if I want to do it with just Excel? Well, here's what you would do. You would take a look at each z-value, negative 1.34 and 1.45. And you can do norm as dist to do the integral of each one of these, and you get the areas below, just like we looked up in the table. Norm as dist is just like looking up in the table. That's all it is. Norm as dist is just doing it out to many, many decimals where the table has been rounded. So this is the area to the left of negative 134. This is the area to the left of 145. So if I want the area between them, I would subtract the two. I would take 92% minus 90% and get the matching answer of 8364 for between. What we are learning is a very important thing here. If I want less than, I'm just going to use the z-value and do norm as dist, because that's what it does beautifully. If I want more than, I'm going to do 1 minus, because that's how you find the area in a probability distribution for more than. 1 minus. If I want between, I'm going to do both of the probabilities and then subtract them. And that's how I do below, above, and between. With all three of these, I can answer any probability question you have about a normal table. Cool. Now, we can flip this on its side. We can actually go a different direction. We can actually go into the table and look out. That is, could you find the cutoff for the top 8%? What does that mean? Well, I like to draw a quick picture to think about that. Top 8%. So, what that means, I always start with a quick picture. What that means is I really have this bar. And if it's the top 8%, 8% of the world is above me. That's all it really means. I am so high in this chart that only 8% of the world is better than me. Or I am in the top 8%, and that's where I fall. And what would be cool is if I could find the z-value, the bar that represents that. That's really the idea. Could I find the z-value that represents that for the top 8%? What bar represents the top 8%? Well, I keep saying top because when I go in my step 2 to the table, I'm not going to the table for 8%. I'm actually going to the left because, one more time, people, remember, the table is always about the left. So I'm actually going to look up, you guessed it, 92%. I'm going to go to the table, and I'm going to look, so this is step 2, I'm going to look for 92%. Now, what's going to happen is you're not going to find 92% of the table. I'm sorry to say. You're going to find a number close to 92%. Remember, these are the actual percents. These are your percentiles. Out here is the z-value that matches it. We're looking at the percentile right now. And the closest to 92% is right here. I do closest. Some people do below or above. I do closest. And so 9207 is the closest I got in the table. That Z value is for 141. 141 would be the number I would think it is 1.41 would be the Z value. And just like that, I have your answer. You want the Z value for the top 8%? Fine. I'll think of it as the bottom 92%, and I'll find that Z value, which is 1.41. So, to summarize, I know from the table the Z value was 1.41. The reason being is the area below was 92%. The area below was 92%, so the cutoff would be, the answer I'm looking for is 1.41. For each of these, this is the answer for this one, for part A. This is the answer for part B. This is the answer for part C. Sorry, for part D. Let me read correctly. And the answer for part E, the one we're working on, is a Z value of 141. That is the cutoff for the 92 percentile. That cuts off the bottom 92 and the top 8. That's what I look at. The bottom 92 and the top 8. They're the same thing to me. 92% below you, 8% above you. That's a Z value of 141. Now, can we get this in Excel? The answer is, of course. We can get this in Excel. You just got to learn about the inverse function. The norm S inverse. I always use the standard. The norm S inverse says, give me probability, and I calculate out the Z value. It's very important. Give me the probability below. If you give me the probability below, I will tell you the Z value you're looking for. And since we're looking for the area below is 92%, that's your percentile, 92%, the Z value you're looking for to the extreme accuracy is 1.405, which when you round is exactly what the table gave. So I call this the NSI, the norm S inverse. I abbreviate it as NSI as we get going. This is how you find the Z value. So same thing here. If we want to bring this faster. If I want the bottom 5%, that means 5% of the area is below us, right? The bottom 5%. I can find it in the table, no problem, or I can use norm S inverse, because that would be the more accurate way to do it. The norm.S.inverse is saying, you tell me the area below the bar, I will integrate and find that Z value. And the answer in this case, the area below the bar would be 5%. If you're in the bottom, that is the area below you. 5% are below you. Notice that very key thing here. I'm using 5%. And that gives me a Z value that is a negative 1.645. So if we look up 5%, we would see it fits squarely between negative 1.64 and 1.65. So it rounded to negative 1.65 in Excel. Sorry about that. Again, if you go to the table, you'll see that negative 1.65 is the one Z value that matches up to 5%. Please, let's make sure we understand both of these. If you want the top 8%, the area below the top 8% is 92, and that's what you got to put in. The area below. The area below in norm S inverse, when you put the area below, it'll search the bar. It'll find the bar that has that area below. It'll find the Z value with that area below. Since you're in the bottom 5%, that is already the area below. And that's why I put the 5% in here. These are the typical 5 questions that are asked. Probability below, probability above, probability between, top cutoff, bottom cutoff. These are the very standard questions anybody asks us about a normal distribution. Of course, you can get a little crazy. You can get a little general, cool question. That is, if you know the score is 8 points below the mean, and it has a Z-score of -2, can you find the standard deviation of that distribution? Well, this question is awesome, but you have to understand a little bit more about what it means to be the standard deviation. You really got to understand the relationship between movement and the standard deviation. This question will be answered in our next video. normal part 2 or normal applications. Thank you guys for watching this video.